We're recording. Go ahead.
So this is where Siri would butter you two up by profusely complimenting you for about 30 seconds.
I
And
like Siri.
after that, we go, this clicker's not working.
Are we timing this?
Go to Miles.
So our objective was to identify and solve the problems of the drag race on the F4U course. The drag races were too costly and too heavy for the airplanes. Our project involved two types of airplanes, the air superiority model and the ground support model. We wanted to optimize the drag links for each type of aircraft. We decided that both would have steel links. They were cheaper and stronger than the aluminum versions. And we kept the I-beam design so that we could eliminate corrosion due to water getting inside the it vastly improves the aircraft because it creates a stronger landing structure for the airplane, and it's a lot cheaper than the original design.
So we should figure out where you want to switch slides.
All right, so for our engineering process, we had to define the problem, which we determined to be the weight of the drag link itself was our biggest problem. So we had to do background research on that, and which in turn, we had to make a plan in turn. So then we had to specify our requirements, which were outlined to us in our the paper we were given. We had to brainstorm, evaluate, and choose a solution. And we had to be sure our solution meets our requirements. And then we had to carry out our trade study and then communicate our results. So the existing design, the drag links were used to prevent the landing gear from folding down when the aircraft touches the ground in a landing, or from folding. Or that. Let me restate that.
It's all good. This is the first part.
Prevent the landing gear from folding up when the plane touches the ground in a landing operation, and from folding down while it's in flight. And when the plane is in a aircraft carrier operation, when planes land, they stop at the end of the runway or the end of the deck, and they didn't have time to reposition them on the deck, so there was a barrier wire that was used to keep the planes from crashing into each other at the end of the runway. And the barrier caught on the oleo strut, and the drag links kept the oleo strut from folding back onto itself on the wing.
Well, that's also Siri. So Siri would have gone through this and made it so the lines are too dark. I should make them white. Made sure that the judges understood our specific process, not just the engineering process.
In connection with any problem, at first we had to discuss as a group and find out all the risks that we were going to deal with, and also figure out ways to overcome those problems. So one of our major issues was being off schedule, and as the project was assigned, we were able to distribute the work amongst our group and also delegate team leaders to instruct those members to make sure that everything was done in time and submitted on time. Also, we were able to meet up with Dr. Irvin, our mentor, who helped us with the geometry, and he was very influential in the three-body diagram process. And pictured here, we have a chart that just distributed the work that was done by all of our members, and we did not want to make sure that one person was doing one job. We had it distributed into a team so that we would have multiple perspectives, and that way we would also be able to complete more work in an efficient manner.
So the next stage of the game was defining the problem again. While we understood that it was hitting the barrier wire, what we needed to do then was figure out exactly what forces were acting on the drag brace part of the plane. Can I have two volunteers to demonstrate that? Ooh, you two can come on up. So what I'm going to have you do is hold this string here, once I get this untangled. This will be representing our barrier wire, and I will demonstrate to you what the main forces at hand were during the situation. I just managed to tangle the string.
That'll be something to make sure. Doesn't
Yeah, I'm just gonna make
happen.
sure that doesn't happen. I messed with the entangle the string. Oh boy.
Here. I'm awesome at knots. Pretend you're doing it.
Well, what happens is you're gonna just stand there and hold the string apart. There you go. So what happens is, imagine these are the landing gear. Imagine this is the landing gear of the plane. What we have here is the oleo strut represented by this piece right here, and we also have the respective lower members and upper members of the drag braces right here, as you can see. The plane would have two of these with the wheel on the outside, and as it came in, the string would make contact likely just above the wheel, and then it would push forward into the barrier while the wire pushed back to slow the plane down and prevent it from crashing into the planes beyond. However, what also would happen was there was a force inward acting onto the oleo strut, not only back. So this resulted in two major forces acting on the oleo struts. One, while this is pushing back, we can demonstrate now. It stretches this way. One, there was a force rotating this backward and pressing against both of these equally. But meanwhile, there was also a force pressing inward, putting greater stress on the inner drag brace. That was actually quite significant. At first, we thought it would be a very similar force, but turns out this became quite significant. So, using free body diagrams, we examined how the forces would be transmitted through the parts. As this was pushed this way, as you can see, there would be force that would rotate this way, creating a torque around this rotational axis that in turn this drag brace right here would react to and prevent it from spinning in this direction. So that would be actually proportional to the radius, the ratio of the radiuses of this brace to the center and the point of contact to the center of rotation. Meaning that because this is a shorter distance right here, this force acting here would be much stronger than the force that the barrier wire was pressing on here. Then in addition to that, not done yet.
Okay.
In addition to that, there was also the force pushing sideways inward that would create a similar force, except it would be reacting this way, and there would be a much smaller distance away. However, we also decided to consider it. This makes the problem solving easier as a force pushing against the drag brace here and not in alignment with the drag brace. So as the wire pushed just above the wheel, that in turn caused the oleo strut to push against the drag brace here. And that created a strong force on the inner part of the landing gear. So then, with those two forces in mind, the back force and the inner force, that those forces could then be added considering this perspective right here. The inner drag brace would have the string would cause the barrier wire would cause a force here pushing it sideways and causing a rotation around this axis. But there would also be the force pushing up, which would spread out among these two. We could consider that again using the ratios of the distances of this point of the force to the point of rotation, and also with the ratio of the distance away from, and also with the vectors of the forces acting in this direction.
Very good.
Yes.
You guys can sit down. You probably could have sat down and
Yeah. Yeah, make sure you
It's okay.
like dismiss them.
Yeah, that's
Yeah,
a good idea.
we'll talk about what we should do at the end. So, Sydney, go.
So outlined in the problem, there are two different possible sizing options. There's the ideal envelope and the acceptable envelope, which have significantly different measurements. According to calculations, if we consider the larger envelope, it is possible to make in theory, a stronger and a lighter piece. But the important thing to consider of that is that if we exceed the ideal envelope, there is the possibility that other additional factors will have to be considered, such as the way that the part fits into the space allotted for it and the way that it moves as a whole with the plane. So in considering it, we had to weigh the weight and the optimum design requirements. And as a whole, we decided that it would be much better to maintain the ideal measurements so as to not cause any additional problems, and the weight differences were largely negligible between the different materials and the different sizings. We initially considered multiple different kinds of shape designs for the piece. We considered solid rods, we considered hollow tubes, we considered the original design of an I-beam, and as well as a potential cross-beam design. In the end, we decided to fully analyze both the cross-beam and the I-beam for the optimum dimensions within the ideal envelope. One of the big important components of not choosing the hollow tube was the fact that it created an open shape, which can cause corrosion difficulties if water gets trapped inside of it. So for air supremacy and ground support, there are two different focuses. For air supremacy, weight is the focus. That you want a lighter piece so that it can be more maneuverable in the air, as well as, and for ground support, you want something that is more cost effective. In the process of considering everything, we decided that considering both the lower and the upper members separately, in order to assure both the minimal weight and the minimal cost for respectively the air supremacy and ground support, was an ideal way to analyze the problem.
Okay, in our calculations, we used the Johnson-Mueller formula, and what that was is that we could calculate the buckling force in which each of our members, our lower and upper members, could handle. Explaining the formula, if you look at rho and you look at I and A are the only two variables that are changing. I is the moment of inertia, and A is the cross-sectional area. As you saw in the previous slide, that was our cross-sectional area. And the other variables in the formula remain absolutely constant as you're changing either the weight, the dimensions, or the length of each of the members. So we didn't have to account for that. And to get FC and strong enough that the members could handle the buckling forces and the stresses put on it, we made rho as big as possible, or originally as big as possible, so that we could have the largest FC buckling force. But as we progressed, we realized that if we use smaller marginal of safety while still being able to handle the buckling force, the members would be optimum weight and optimum cost.
So then what we handled next was a program right here that would actually arrive at our solution for us. There were lots of different variations. We had decided we would use the I-beam. Yeah, we'll make it run in a second. We're supposed to make it play. Well, not yet. I was going to explain something.
I was going to see if that thing can't work. Oh, keep
I
going.
guess not. Well, anyway, oh, no, I lost my train of thought. Way to go, Krista.
Why is he not playing?
That's
I
the
don't know.
question.
Here.
Oh, that's it. Well, anyway, the point is that there were a lot of possible combinations. We decided we were using what materials we would use, and we decided what shape it would be in the I-beam, but there were still a lot of combinations to sort through, particularly with the dimensions of the I-beam, which is what we wanted to try and change to make it optimal for the situation, specifically for weight and the strength of the member. So what we could do is by using the variables that were constant to the material and to the situation, we could, we could, oh boy, this is bad.
Okay.
Where are my note cards? I had a plan for this.
So, if there's a train wreck when we're there.
Oh no, I know.
It's not going to be
I
a
know.
train wreck.
No, I know.
It'll just stop at the station maybe and then keep going.
Oh no, I know.
So what we did is we had a looping program that would run through every single combination and increment it by 1/100 of an inch. And what this would do is it would sweep through all the possible variations of the dimensions of the I-beam while running it through the Johnson-Euler buckling formula and ensuring that it had the sufficient strength to withstand the forces that it would be up against. And it's gone now. That's a shame.
Well, we know what's going on.
We know what's going on. So what is happening here, as you can see, is the webbing, which is the middle part of the I-beam, is expanding outward over and over again as that part of the dimensions is incremented over and over again by hundredths of an inch, by 1/100th of an inch. Meanwhile, as the webbing is incremented over and over again, when it reaches a certain maximum, specifically the manifold, I should find out what that's called. The cross-sectional envelope, not manifold, what's a manifold?
It's okay.
The envelope, when it reaches the maximum envelope, it will shrink back down and the width of the flange will be incremented. When that is incremented, then it will start expanding the webbing again by 1/100th of an inch. This happens over and over again. In fact, we end up reaching calculations in the tens of thousands. That's for all of them. For just this one, we reach 15,000 calculations, but this is just for one combination. Specifically, the lower member meant the situation for air supremacy, meaning it has to be much lighter and made of steel. But we checked all possible configurations, reaching calculations and combinations of materials and dimensions of the I-beam reaching into the hundreds of thousands, 250,000 to be exact. And what that did is, as we checked through the program, not only were we checking for strength, we were also checking for mass. If any time we found a configuration with a lighter mass than one that we hadn't found before, we would store that and for later and check other ones against it until we found the one with the lightest mass, which is what you see here. That's it.
Who's next?
Oh boy.
Here. Oh, to make a 35 finally? Here, you keep going. You totally know what's on your slide, right? No, next to you.
Here, Nico's up there. No, next is me. It's up there on the.
Oh. Okay.
Here you go.
Okay. In our Johnson-Euler analysis, our final, these are the weights. As you see up here, these are the weights that you see for NA. It's, what was that name?
Not applicable.
We couldn't.
Yeah,
We couldn't make it happen.
That's something else.
it did not
That
fit
is the
within our
general term of NA.
ideal envelope. As you can see, we found different masses for the lower and upper members, and this is why our design is the best and will give you the most strength for the cost and for the weight.
After utilizing the program in Excel, we decided.
Here, you keep going.
All right. We put them in a Excel document, which put all the numbers in, all of the masses in, and we got the total cost of one unit, and then we put that in and we compared it. We put all the masses in, and each one had its own page. So we compared the steel and the aluminum, and we got the price for one unit with all the stamping and all the material costs. And we put it in one Excel document. We compared all of the masses with the price. As you can see, and then we have it in cost of 1,000 units, so we could see the mass and the price, so we can weigh both options so we can determine which is the most, which is the best mass to use.
What we did to analyze, to take all our data and analyze it in a presentable form, is we created a trade-off matrix. As you can see, the best is in green, and the worst would be in red. As you can see, the I-beam got the best score, are modified in our trade-off matrix. We assigned the least weight with a number and multiplied it by, should I go that in depth?
Well, I think you should just talk about how we weighed each combination, and this is one example of that for air spread with the low number, and that we use that to total up exactly which thing.
And we used to consider all the factors.
Yeah.
But with higher weight to some
Yes.
in particular.
I think I can
I think we should also talk about. Yeah, I got it.
I think
yeah, how we
weighting
weighed all the
factors.
features.
Yeah, say which
And how
which
it
one
is
was the most.
Yeah, and how it changed the calculation.
I don't have no proof yet, so I'll do that. What to take away from this? We successfully defined and understand the problem in context. We made a plan to analyze the requirements. We evaluated and chose solutions to meet the requirements. And after over 250,000 calculations and various studies to pick the exact right race design for you, we found the best solution possible. We have the answer, and it is this.
Can we show our solution?
So it was supposed
I
to,
think we should
the,
show our solution.
the solution was supposed to show up on the program. Actually, that was it. On the program, that was it. Just a slight change. Even though it wasn't running, that was
the actual solution.
Do we know
You can
to?
show a model.
Here, you
I think
can
that
probably
was
stop it at this
Our
point.
model.
I did think that.
We'll just cut